Hello everyone, welcome to Sweetie Speaks official YouTube channel. In the previous lecture, we learned about von Neumann architecture. In case you missed that video lecture, I request you to please go through that and then come back here so that you get a better understanding of Harvard architecture. I will share the link for the von Neumann architecture video lecture in the description box. Let's get started. If you remember, in von Neumann architecture, we told that instruction and data are stored in the same memory. The major difference between von Neumann and Harvard architecture is that in Harvard architecture, both your instruction and data have separate memory, not the same memory. So you will have instruction memory separate and data memory separate in case of Harvard architecture. Since they have different instruction and data memory, you also have different buses for data and instruction. Data bus is used for data transfers and instruction bus is used for fetching the instruction. Again, since you have separate buses and separate memory, you can fetch the data and fetch the instruction at the same time. If you remember, in von Neumann architecture, we had discussed about a limitation called as bottleneck, in which you can't fetch instruction and data at the same time, because in von Neumann architecture, instruction and data share the same memory and same bus. But here, both the memory and buses are separate. That is why instruction and data both can be fetched at the same time in case of Harvard architecture. Due to this, the processing is faster in Harvard architecture. Now let's see how Harvard architecture is represented. The first component is ALU, which is arithmetic and logic unit. We had discussed about this component in detail in case of von Neumann architecture. It's the same component. Let me give you a gist once again. ALU stands for arithmetic and logic unit. It can be called as a computation unit of your processor, where a lot of computation and calculations happen. It performs operations like arithmetic, which can be add, subtract, multiply, divide, etc. And it performs the logic operations like AND, OR, NOT, XOR, etc. In addition to this, it will also perform the comparison operation, less than, equal to, such kind of operations, as well as bit shift operation, shift left, shift right. All these kind of operations are performed by your ALU. Then you have a CU, which is control unit. As the name suggests, it controls your processor. So it contains a lot of control signal. One example is, this example we have also discussed in the previous lecture. Say you have a main memory and you want to access that memory. To access that memory, you first need the enable signal to be high. This enable signal is controlled by your control unit. Similarly, it carries a lot of control signal information, as well as it carries the status signals. Now, say for example, I'm transmitting a data. Data can be transferred successfully. There can be some error. So this information is carried in the form of status signals. These status signals are also carried by your control unit. Along with that, it also has registers, as we had discussed in von Neumann architecture. Registers were MDR, which was memory data register, which carries the data which needs to be transferred to and fro from the memory. Then we had memory address register, which carries the address. Then we have PC, which is program counter, which carries the address of the next instruction. All these registers are also present in the Harvard architecture. We are just not showing it in the representation. And then again ALU, CU, and your registers together form a CPU, which was central processing unit, which can be called as the brain of your computer. This ALU and control unit are connected to each other with the help of the buses. Then you have instruction memory, which carries the instruction information. And then you have data memory, which will carry the data. Since it's Harvard architecture, both instruction memory and data memory are separate. And we had discussed, since both memory are separate, the buses also will be separate. So these are instruction buses and these are data buses. Now let's talk a little about the buses, since it is different in Harvard architecture. So if you remember, in von Neumann architecture, we discussed there is a data bus which carries data, there is address bus which carries address, and there is control bus which carries the control information. In case of Harvard architecture, you have two different buses for instruction and data. So you will have instruction bus which will carry your instruction. You will have instruction address bus which carries the address of your instruction. You have data bus which will carry the data information. You have the data address bus which carries the address of data. To just revise once again, you will have separate buses for instruction and data. You have instruction bus which carries the instruction. You have instruction address bus which carries address of instruction. Data bus which carries data. Data address bus which carries the address of data. Then you have the input device which will provide input to your CPU. And this input device, some examples can be keyboard, mouse, microphone, and they provide the input to your processor. Then we have output devices which will take the output of your processor. The example of output device can be monitor, where you can see the output. It can be printer. These are some example of your output devices. This is representation of Harvard architecture. Now let's see what are advantages of Harvard architecture. As we have discussed, in Harvard architecture, we have separate instruction and data memory. Since the instruction and data memory are separate, the processor can access both of them simultaneously. Due to this, this architecture has faster processing and the data retrieval is more efficient in case of Harvard architecture. Another advantage is reduced resource conflicts. Again, since the instruction and data memory are separate in case of Harvard architecture, right? Since these are separate, that is why you will not see any resource conflict, because there is a separate resource for carrying instruction and separate resource for carrying your data. Now your data and instruction memory are independent from each other. Since they are independent from each other, it allows for more effective cache memory usage, because the cache misses will reduce since you are storing the data in a separate memory. Because of this, because of reduction in the cache misses, again the speed and performance is increased. Then there is enhanced parallelism. Parallelism means instruction can execute in parallel, because you can access instruction and data simultaneously since both are in the separate memories. Because of this parallelism, this architecture is more useful for real-time application like digital signal processing, wherein you are doing the real-time processing of the signal. Then it has enhanced security. Why do we have enhanced security? Because the instruction and data memory are separate. Due to this, you have enhanced degree of security against certain type of attacks, for example, buffer overflow. So if there is buffer overflow in instruction memory, it is separate from data memory. So there is no buffer overflow necessarily in data memory when there is a buffer overflow in instruction memory. So when someone is trying to threat your security using buffer overflow attacks, these kind of attacks are reduced in case of Harvard architecture due to separation of your instruction and data memory. Now let's see some of disadvantages of Harvard architecture. First one is increased design complexity. You have separate memories, you have separate buses, the number of buses also increase, due to which the design complexity increases. Design complexity increases means the amount of hardware required will also increase, which in turn will increase the cost. So you have higher cost. Then there is limited flexibility. Why there is limited flexibility? Because at the runtime you can't modify instructions. Why? Because instruction and data are stored in separate memory. That is why modifying instructions at the runtime becomes very difficult. This limitation can make certain type of programming more difficult or very impossible to implement in case of Harvard architecture. So applications wherein you want to modify instruction at the runtime, they can't use Harvard architecture due to this limitation. That is why it is not suitable for general purpose processors. Why? Because there is increased cost. And in case of general purpose processor, we first of all need simplicity. We don't need complexity. And general purpose processor are very cost effective. So you can't have the higher cost. That's why this Harvard architecture is not suitable for general purpose processor like your personal computers and laptops. So in case of personal computers and laptops, we use von Neumann architecture. Then there are code size limitation. Why? Because you have the fixed instruction length. Because the instruction size is fixed, the instruction memory is fixed. That is why there are very limited code size. You can't have a lot of adaptability to change your code size because your instruction memory is limited. Both your instruction and data memory are separate. So say for example I need an application wherein I need to use the more instruction memory, but I have limited instruction memory. So such kind of applications which have larger code bases can't adopt Harvard architecture. Now let's see some of the applications. Applications come from the advantages itself. The first application of Harvard architecture is DSP. DSP stands for Digital Signal Programming. Now, if you remember, we said that DSP is an example of real-time application. Real-time application means you are analyzing or you are processing the data in real time. Such real-time applications need to execute faster. You can't execute it slower because these are real-time applications. So efficiency and performance matters a lot in such kind of applications. That is why Harvard architecture is more suitable here. Hence, it is widely adopted in your DSPs, which is digital signal processing. This is the first application. The second application is microcontrollers. Now we had discussed that even von Neumann architecture is also used in some of the microcontrollers where your cost plays a major role. Now in some microcontrollers, say for example, there are certain microcontrollers which are using IoT, Internet of Things. Here you need good performance. For good performance you can't use von Neumann architecture. That is why in such applications also your Harvard architecture is more suitable. The next application is ASIC. ASIC stands for Application Specific Integrated Circuit, which is the circuit designed for a specific application. Now, these applications, which is ASIC, also need good performance. Again, since they need good performance, you can't use von Neumann architecture. That is why we are using Harvard architecture. The next application is FPGA based processor. So there are some processors which are based on FPGAs. These kind of processors also use Harvard architecture. These are some of the applications of Harvard architecture. I hope with this you have now understood Harvard architecture. In the upcoming lectures, we will see a lot more topics on computer architecture. To stay tuned, please subscribe to Sweetie Speaks official YouTube channel. Thank you.